Okay, so today we have Ghaemidizicheh. I'm sorry for the pronunciation. And he will talk about transport effects in non-reciprocal tight binding models with gain and loss, as you can see. So whenever you're ready, go ahead, Hamid.
Yes. Hello, everyone, and thanks for joining this talk. I would like to appreciate in the beginning the organizer for organizing these these virtual seminars. My name is Ghaemidizicheh from the University of Texas, Rio Grande Valley. And today I'm going to talk about transport effects in non-reciprocal tight bonding models with gain and loss. And the picture that you can see in the background is in Lancaster. The relation is that I did the research when I was in Lancaster University working with Professor Henning Schumacher. Okay. Okay, in this presentation, so first, I should say that you hear a lot about the transfer matrix, because this is the main part of the research work. So I'm trying to give you a motivation that why transfer matrix is a powerful tool, the simple and but powerful in non-Hermitian physics. So I just mentioned about the application in continuous systems, but the main part of my presentation concentrate on tight bonding models. And so the main idea of this talk is that show the compatibility of transport effects in non-Hermitian non-reciprocal systems by considering tight bonding models. So, and these are the topics that I try to cover in this presentation. First of all, I will show that how we can find the conditions for the transport effect in such a systems. Then I identify which effects are compatible and linked with each other. The transport effects I will mention, but just if I want to just mention to that here, there are, I mean, such a transport effect such as reflectionless, invisibility, or coherent perfect absorption, which I will talk about them. And then I want to determine by which level they can be tuned independently. These are three questions or the comments that I try to answer in this presentation. Okay, the non-Hermitian physics have a long tradition in describing a state with a finite lifetime, and so as you know that with these topics appears in the vast range of applications. So here I skip history, the introduction, because since this virtual seminar, a lot of experts just describing and give the physics and the mathematics behind it. But just I want to mention this nice review paper, as you can hear, that which is a very good references for specifically students and our junior researchers such as me to see a lot of applications in non-Hermitian physics, from the photonics models to the acoustics, and also it provides a good references that everyone can find it. But among these applications, there are two parts that I'm interested in. The first part is non-Hermitian photonics, that study the optical wave propagation in symmetric gain and loss photonic models. So there are some phenomena that you can see when you considering non-Hermicity in optics. For example, unidirectional invisibility is one of the transport effect that I'm going to talk about. The coherent perfect absorption, which is kind of anti-lasing in the systems. And if you just doing the studying the non-Hermitian physics in nonlinear optics, then you can find lasing conditions. So I'm sure that there are a lot of references that I need to add here, but these are just in my point of view, the most important. But each of these topics are well known, and there are a lot of works have done. And the second part that it is kind of new is about non-Hermitian topological models. So this is the non-Hermitian counterpart of the topological models that the people known from decades. And you can make the topological model non-Hermitian by introducing on-site gain and loss in topological tight bonding models, or by model them with asymmetric hopping amplitudes. The second one means that the system is non-reciprocal, and you just using the imaginary gauge field to change the couplings and make them non-reciprocal. So by using one of these techniques, you can make your system, your tight bonding system, non-Hermitian, and then you can see some phenomena that are absent in the Hermitian topological model. The famous one is non-Hermitian skin effect that we had talked in these seminars. Just to remind you and just give you a short introduction that what is non-Hermitian skin effect. So in this effect, all the eigenstates under open boundary condition might be considered as edge modes, since they are exponentially localized at one side of the lattice. This is coming from the asymmetric hopping. So the non-reciprocity plays a very important role in the model for seeing the non-Hermitian skin effect. And so you can see this effect both in classical system, for example, by considering the non-reciprocal robotic metamaterial structure, or by studying the system of spring and mass. So you can see these effects. In both cases, the couplings are non-reciprocal, and there is asymmetric in the systems. But the famous one that everyone the famous one that kind of introduced this effect is in quantum mechanics, when they studied the SSH model with the non-reciprocal couplings inside the cell, and then you can see that the Bark state just localized to the left side. But so this is the important effect that you can see both in classical and quantum mechanics. And remember that the other part was in the non-Hermitian physics that I was interested was topology, non-Hermitian photonics. So the combination of these two applications, I mean the non-Hermitian photonics and non-Hermitian topological systems, leads to the new research area, which is called topological photonics. The idea here is to investigate in single particle band topology in photonic systems. So, and the motivation that why these models are important is that we can, using the topological edge states, to guide and route light in a manner that is robust against the scattering by disorder. It is coming from what we have done in the Hermitian topological system, but now you can use it in the photonics platform. The presence of absorption and radiation in these systems make the system non-Hermitian. So it means that it provides a very good platform to study the non-Hermitian physics, specifically to study the topological effects coming from the non-Hermicity. And nowadays, there are a lot of models that people are studying, specifically those include linearity. So as you can see in the picture, the first row are the platforms that you can study the topological photonics. So each platform is a structure, is a tight bonding structure. One of them are in 2 dimensions, one of them is just a chain in 1 dimension. The second row shows the effect that you can see in each models. And this third row is the applications that you can see that it has a lot of application nowadays. So this is the motivation of this this is my motivation that to study the transport effect in such a system. since you have a topology and the optics, then you can combine them and see what boundary condition or what transport effect that you can find in these systems. So, but in my study, I just consider a very simple one. These models are more complicated, but at the end, I will mention that we can kind of generalize the method that can be helpful for studying these topological models. Okay, so the question is that why transfer matrix? Why we need transfer matrix? So I try to just look at the continuous model. That why transfer matrix is important. So this reference that I show you is also a nice review paper that you can find the transfer matrix, the definition, the application. But here I just give a very simple but well-known definition of the transfer matrix that we all know from the quantum mechanics. So in the continuous model, if you consider the scattering potential, which satisfies this integral, or I can say that this is the finite range potential, then, for example, you can solve the Schrodinger equation and find a solution. And the solutions the asymptotic solutions are satisfying this relation in the infinity and minus infinity. The infinity means that it is out of the range of the potential. So the potential is zero at this infinity. So, and you can see that this, for example, the Schrodinger equation in classical or the Helmholtz equation in optics, the solution of that satisfies these relations. Then the transfer matrix is given by the 2x2 matrix that relate the amplitude on the right side to the one on the left side, the amplitude in the plus infinity to the one in the minus infinity. This is a very basic definition of the transfer matrix, but there are more complicated and more technical definition that you can find in the references, and the Professor Mostafazadeh gave talk in nice talk in these seminars. But here, just to mention for those who are not familiar with transfer matrix, that in the continuous system, this is the very basic definition. So usually people introduce or define the transfer matrix for the linear system, but you can extend it to the nonlinear systems, which include the nonlinearity. So there is a nonlinear generalization of the transfer matrix, and it is important because in most models, specifically in optics, we have a nonlinearity. For example, the Kerr nonlinearity, and if you want to use the transfer matrix, you need to at least have a picture of what is the transfer matrix in nonlinear systems. For example, recently here in Texas Rio Grande Valley, I did a research with Dr. Ramazani that in this research we consider the optical setup involve a nonlinear material which producing or which generating the higher harmonic waves, and it's located on the left side of the periodic structure, and by using this photonic structure, we can see that the photon comes from the left side, localized inside the defect layer. This green is the defect layer, and from the photon coming from the right side is perfectly reflected. So this is kind of shows the asymmetric localization of the photon inside the system. And we solved the problem in the theoretical way and the numeric way. And in the theoretical part, we use the nonlinear transfer matrix to solve the scattering problem. So this is kind of the advantages of the transfer matrix, that you can find the solution of such complicated scattering problems and show the effects. But why transfer matrix in tight bonding models? So this is kind of new. The people in condensed matter knew about the transfer matrix, but here I want to give you a technical way to find the transfer matrix for tight bonding models. So this work is based on this reference, which introduced this technical way. So the benefit of that is that you can find the transfer matrix for a complicated structure. And so it's going to help you to apply the method that I introduced here for the topological photonics platform that I showed you in last slide. Okay, in two slides, I try to show the technical way to define the transfer matrix for tight bonding model. So first of all, consider a very general structure that I showed you here. The Hamiltonian of this structure is given by this formula. Looking at the Hamiltonian, inside the Hamiltonian, you can see Q. The Q is introducing the internal degree of freedom of the system. For example, if you have a spin or orbital in the system, so you can add this to add them as a internal degree of freedom inside the Hamiltonian. This L from 1 to R kind of show the range of hopping. For example, here L equal to 1 shows that there is a hopping between one side to its neighborhood, and for 2 there is a hopping between this side to the next to 2 next neighbor. So this is coming that what range of hopping you want to consider in your problem, and this n is just define the number of the sides. So there can be a complex hoppings between these sides, and each degree of freedom for each side can couple to the other degree of freedom. So you can consider this picture as a combination of nodes and links. So, but I don't plot them here. But if you just think about the coupling as a matrix, so you can get the idea that what I mean, that there can be a complicated links in this material, in this structure. Okay, the idea is to bundle the M adjacent sides and change the system to the kind of super model or the super lattice. So it means that we bundle some sides, and by doing this, we kind of change this Hamiltonian to the supermodel counterpart. I mean, maybe super is not a good terminology because, but the super means that instead of the model, you can have a bundle of the models. And then the equation coming from the Hamiltonian, the Schrodinger equation is given by these equations. Now JR and JL are the hopping matrices that includes TL and TR, the small TL and TR. And K is kind of the on-site potential for our supermodel. And this psi n is just defined by this column matrix. Okay, and then if you consider the periodic system, you can find a block Hamiltonian correspond to this model, the block Hamiltonian given by this equation, and Kx is just one of the dimension, and the inside of each J and K, there are other dimensions that are periodic. And if K is equal to K dagger and J are equal to JL, it means that you can consider the system as a reciprocal system, and a system which doesn't have any gain and loss. Then the system is Hermitian. So the Hermicity, the definition of Hermicity is coming from this line. But the benefit of this method, as I mentioned, the people knew about the the transfer matrix method in condensed matter. But this method is better because you can find the transfer matrix for the singular J. So this is the component, one of the constraints that you can remove from the system. And this J is important, especially the rank is very important because its rank denotes the number of the bonds between adjacent supercell. So maybe it's not very easy to see what's the meaning of the rank here in this system, but in the example, I try to show you what the rank means. Also, the rank defines the dimension of the transfer matrix. Okay, if we consider the non-reciprocal system, then we can use the reduced singular value decomposition to write the coupling matrices as this equation, the product of three vectors, which the middle one is the diagonal and each one is called the singular values. Now the R is defined as a rank of J. Also, we assume that our supercell are big enough that J is nilpotent of degree 2. It means that the rank of the J, the coupling matrix, is less than the total degree of freedoms in each supercell. And following this relation, you can find kind of orthogonal basis that you can expand your wave function in terms of them. So this is this alpha n and beta n are given by these matrices, and they goes from 1 to R, which is the rank of J. Then by considering the green function of the system, you can reduce the Schrodinger equation to these two equations. These two equations kind of relate the different modes in different sites. And this curly J A B, this is just a notation that I define in this line. So you can see that the curly J A B is A dagger GB. And in general, this is the matrix R by R matrix, and this is complex. Then by introducing this wave function, which includes the modes given in this form, the transfer matrix is the matrix. As you can see under the arrow, the transfer matrix is a matrix which relate the phi n in each in one lattice to the neighbor one. And in the picture, you can see it's kind of relate the modes that we introduced in the expansion of psi. So the transfer matrix of the system can be given. And so this is kind of technical way to find the transfer matrix, but it is very useful, but because you can apply it for a very general form of the structure, even for those that it is not easy to find the transfer matrix. So the transfer matrix of the system is given by 2R matrices. The R is the rank of J. Okay, let's look at the elements of the transfer matrix and specifically see what's the determinant of this transfer matrix. So in the Hermitian case, as I mentioned, the black Hamiltonian is Hermitian. So these curly J, A, B are also Hermitian. So remember, they are these curly J are the matrix. In the case that R is equal to 1, they are just a number, and it shows that they are a real number. Also, if you just look at the PT symmetric system, that PT is given by this operator, U is a unitary operator, and K act as a complex conjugation. Then if the system respects the PT symmetry, or it's invariant under the PT symmetry, then you can find a relation on J and K. Remember that J and K was the coupling matrix and the on-site potential. And this leads to this relation for curly J, A, B. So why it's very important? Because if you just evaluate the determinant of the matrix, the transfer matrix, the determinant is given by this relation. And for both cases, when the system is Hermitian and the PT symmetry, you can show that the determinant is just a phase, and its absolute value is 1. So it shows that for the Hermitian system, the determinant of transfer matrix is 1. And if you just remove the hermicity from the system, for example, make the system non-reciprocal, or just adding the gain and loss to the system, so the determinant is not more 1. So, and this is important. Why? Because if you just consider the case when r equal to 1, it means the rank of the coupling are 1, then the transfer matrix is a 2x2 matrix. So this is a very familiar form of the transfer matrix that people know. Then you can show the bulk states localized on the left boundary for the system if the determinant, the absolute value of the determinant less than 1. And it's localized on the right boundary if the absolute value of the determinant is larger than 1. So it means that the existence of non-Hermitian skin effect can be deduced from the value of determinant. So it is important because by looking at the determinant of the transfer matrix, you can find the skin effect. And you can predict that the behavior of the bulk states in the skin effect just by looking at the value of the determinant. I'm not using this kind of fancy and technical method for driving the transfer matrix in my presentation, but I will give you the idea how we can use it for generalizing. But I want to show that kind of application of this method and show that it's kind of useful to use this method for finding the transfer matrix for some structure that seems not very straightforward when you want to drive the transfer matrix. For example, you can consider the ladder lattice, which is studied in this PR paper. And the equation of the lattice is given by these two lines, and U prime and U are the couplings. And if I just doing the techniques for bundling the sites, then I can find that in my system, the J, L, and K, which I mentioned, are given by these 2x2 matrices. The rank of J is 1, since you can get one column from the others. And then by using the method, you can just find the transfer matrix of the system. So otherwise, it's not very, you can do it, but this method is just give a kind of protocol that you can follow it and get the transfer matrix easily for such a system which has more complicated links than, for example, SSH model that everyone knows about. But one thing that we found that, for example, if you are doing the same method as the singular value decomposition, and just by playing with the equations that I skip here, then you can find that in the point of transfer matrix view, this ladder lattice is similar to the one that it's very famous, and this is the SSH model. So this model is this model is, if you look at the transfer matrix of this model, you can just forget it and then instead looking at this model. And if you're just looking at these couplings, you can see that there is a non-reciprocity in the models coming from the gain and loss inside the system. This I gamma and I gamma prime are the on-site potential, and you can consider them as a gain and loss, depends on the value of the imaginary part. And so this is first of all, it shows that this model, the SSH model, which is non-reciprocal, is very important to study because you can kind of reduce a lot of model to this one. And also it shows that the transfer matrix is good because in the following you can see that transfer matrix can give you even the spectrum of the system. So it is good because instead of study this model, you can just reduce to this and get a result. Okay. Now let's look at the model that I want to discuss more about that. As I said, the SSH model is very important. So I'm looking at the kind of same model here. This is the general, but this is the simple. This is the general, but the kind of important model that you can study here. So this model, as you can see, is constructed by this chain. At this chain, so you can see that the couplings are asymmetric. So there is a non-reciprocity for each side. The couplings are shown by U2, V1, U3, and V2. So this is the very general form of the couplings inside the system. And this V1, V2, and V3 are the on-site potential that they can be complex. So in our model, as I said, since the non-reciprocity is important, so I consider the non-reciprocal model that can give us the non-reciprocal non-Hermitian transport. But the non-reciprocity means here means that at least one of the couplings are dissimilar to the other. So there is an asymmetric or there is a non-reciprocity in the system. And also I consider the on-site potential is complex on-site potential, then you can introduce the gain and loss through the system. Okay. So the difference is, for example, the thing that is important here is that I need to attach the model to the lead from both sides, from the left and from the right side, because at the end, I want to look at the transport effect or transport boundary condition inside the system. So what is the lead? What's the meaning of lead here? The lead is the same. It's something with the same structure. It is with the same tight binding structure. But here I put some limits on the couplings and on the on-site potential of the lead. So this is kind of that we model-less leads in featureless wideband limit. So what does it mean? It means that first of all, the couplings of the leads are symmetric and are all equal to W, as you can see. And we assume that this W is negative. So this is the couplings for the left lead, or for the system if n less than 0, which is showing the left side, and n larger than n, which is showing the right side. The second condition that I consider here to make the lead featureless is that I tune the potential to the band center. So it means for each side of the lead, I put Vn, the potential equal to the band center, which is E here. So if you look at the equation, you can see that these in the equation, the left side goes just with the first term, and at the second and the third term, we just have W as a couplings. If you do this, then you can introduce the propagating wave inside the system. So the propagating waves, which defined on the lead sides, are given by this relation. The first line defined are introduced to propagating to the right. For example, if you consider this side, and the left one introduced to propagating to the left. So I just figure out that I need the pointer. Okay, anyway. Yes, these are the propagating waves for propagating to the right and propagating to the left for the first line and the second line. Just look at the first line propagating to the right. So here, yeah. Okay, then I find. Okay, here the psi plus and psi minus are position independent amplitudes. They don't depend on the position of the system. The only dependence on the position coming from these phases. N is the number of the sides in the lead, and this n plus and n minus are the offset that you can tune for each lead. This is kind of the U1 gauge freedom of the system. It means for each lead you can tune the n plus and n minus, then you can find the propagating waves for each side inside the lead. So this is kind of techniques that you want to use to make sure that the lead doesn't affect on your system, then you can say that every properties that I can find comes from the lattice itself, not from the lead. Okay, two more conditions is that the boundary couplings from the lead to the system match perfectly. It means that these couplings and these couplings are equals to W this equals to W. So it means that then one can include the first side of the lead into the system. And the second one is the only parameter, as I said, the character in the lead is W. And so you, by just considering this technical assumption, you can make sure that there is no effect, no transport effect coming from the leads. And what you can find is just more addressing the properties of the system itself. Because when you want to apply the system or the method in some photonic system, then there are many ways that you can prepare the leads. You can find a wave to the system, but this method is kind of general because it can predict. Even in that setup, you can see such effects. Okay, just look at the transfer matrix of the system. The transport effect of the system can be characterized by the real space transfer matrix. With the real space transfer matrix, I mean the transfer matrix just describing the chain without the lead. So the transfer matrix is the product of the transfer matrix for each block. So this M2, M1 is the defined transfer matrix, which just relate each side to the neighbor one. And then by using this matrix product, you can get the transfer matrix of the whole system. And each Mn is given by these 2x2 matrices. So you can use the method that I showed you to find this transfer matrix, but even without using that method, this is not very hard to find that transfer matrix just by writing the equation. Okay, in the propagating state basis, now I want to look at the transport properties. So I need to just define the transfer matrix which relate the propagating wave on the left side to the ones on the right side. As I showed you, remember I showed you the transfer matrix definition in the continuous system. The method that I use here is similar to that one. So this curly M is kind of the transfer matrix in the propagating state basis. Is just relate the sides in the lead. And you remember, according to our assumption, you can consider this side in the systems, this side of the lead inside the system. So this curly M is just the transfer matrix which relate the propagating waves on the right side to the one on the left side. Okay, and then if you using this propagating state transfer matrix, you can characterize or you can find a different boundary condition for your tight bonding models in terms of the transfer matrix. So this is exactly what the people do in the continuous model, in the optical model, but here you can also give a kind of characterization. In the first column, so you can see a different boundary condition. In the second column, I give you a definition of them. And in the third one, these boundary conditions given in terms of the transfer matrix or their interest. So this is kind of, it just shows that by each effect, put a constant on the transfer matrix and its element. So for example, for the open boundary condition, which you apply this boundary condition that the states on the boundary are 0, then the transfer matrix can give you the condition, the boundary condition. For the periodic, if you have a periodic in the systems, then the determinant M minus EIK can give you a dispersion relation of the system. Then these are the boundary conditions that are also well known in the optics. So for example, the quasi-bond it means that there is just a purely outgoing waves. And and for those energies that they are real, it means that the imaginary part is zero. Then instead of the quasi-bond, you can have a lasing state. And for scattering zero, as it's clear from its name, it means that there's just purely incoming waves. And for the real energy, it is just a CPA or coherent perfect absorption. Also, you can see the reflectionless and transparent inside the system. The combination of these two effects can give you invisibility from the left or from the right to the source or detector. So in this picture, I schematically try to show which effect means in our system. But the transfer matrix is not the only way that you can characterize the system. You can use the scattering matrix instead, and which scattering matrix is given from this definition in terms of the transfer matrix. These are T prime, T and R prime are just the reflection amplitudes, and T prime are transmission amplitudes. But also you can use the other formula or other method to find the scattering matrix of the system. This is given by the Green function of the system, and inside the Green function we have H effective, that it is H effective include the self energy of the lead. So this is the method that you can use, and even if you use this one or the other one, so you can get the same result, and you can characterize the different boundary condition by putting constraint on the transfer on a scattering matrix. Okay, now look at the energy constraint on the system. For example, for closed system with open boundary condition, the equations coming from the transfer matrix is given by this equation. And this is a kind of implicit equation in terms of the energy, and the solutions are in general discrete and complex, as we know in the non-Hermitian topological models. For the periodic boundary condition, in terms of eigenvalues of the transfer matrix, the period boundary condition are given by putting each of eigenvalue equal to 1. These are the eigenvalue of the transfer matrix, and at the point that eigenvalues are the same, then you can have exceptional points. And this equation, which I showed you in the table, it gives you an implicit dispersion equation in the periodic system. For the quasi-boundary state and scattering zero, each equation coming from the elements of the transfer matrix can give you the energy of the system, and such as the open boundary condition, the energy are complex and discrete. If the imaginary of En equal to 0, for the real energy, there is a stationary lasing state and its time reversal, which is coherent perfect absorption. So in this diagram, just as an example, I show that the different energy for open boundary condition with green quasi-bond is defined by the blue line. The scattering zero is given by the orange one. And this segment, this curve is just coming from the periodic boundary conditions. So by just using the transfer matrix and solve the implicit equation, which is not very hard, which is easy, then you can find the spectrum of the system. Okay, now the next step is to find the relation between, for example, the different transport effects, and also see what's the effect of non-reciprocity on these transport effects. So first of all, I'll consider the effect of non-reciprocity. In the non-reciprocal system, we have this condition on the scattering matrix. And on the other side, it means that left transmission amplitude is not equal to the right transmission amplitude. By looking at the transfer matrix, if you find the determinant of the transfer matrix, then you can see in the system, which is not reciprocal, the transfer matrix is not 1, and it is given by the ratio of the couplings. The question is that does non-reciprocity make constraint on the boundary condition? So for answer this question, you can look at the reciprocal counterpart of the system. So if you want to look at it, then you can scale these couplings in the system, and this scaling just leads to the scaling of the transfer matrix. Then you kind of transform your system to the reciprocal one. But why I'm doing this? Because it shows that all conditions where transfer matrix element have to vanish are identical in both reciprocal and non-reciprocal system. This is kind of show that non-reciprocity doesn't have any effect on the boundary conditions that I showed you. But but if you want to look at more details, the transfer matrix of the system can be given by this formula. So here MC is the transfer matrix at just one block, and U is the Chebyshev polynomial of the second kind. This L defines the size of the system. It is 2n in our system. And as you can see, the only place that the determinant appears is just here, coming from the D. D is the determinant of the matrix. So this equation shows that, first of all, you can scale the transport from the left to the right by a factor of D, and also in the opposite direction is scaled by D over minus L2. So it shows that the non-reciprocity just scale the amplification from the right or from the left. But all characteristics that rely on vanishing transfer matrix element are the same in the non-reciprocal and reciprocal variant of the system, because for that you need just to look at this relation in the bracket, and this relation doesn't have any link to the determinant. Okay, but if you want to look at the system more closely and just put some value to the couplings and to the potential. So first of all, as I said, I'm looking for the asymmetric couplings, but the couplings are not asymmetric in all links. So indeed, I just suppose that the U and V prime are the same and equal to the W. This is the way that I want to consider the ballistic couplings to the lead, because I use the perfect match coupling to the lead, which is given by the W. And to satisfy that condition, I need to put more constraint on the couplings of the system. And the constraint is that U and V prime are the same. But I define two parameters that play a very important role in our calculation. One of them is D, the determinant of the matrix, is given by U prime over V. It's kind of defined the non-reciprocity inside the system. The other one is kappa, which define the topological characteristic of the system. If you just, I mean, it's coming from the non-Hermitian topological models, that these parameters can show that in which phases the system is topological or not. So by using these two parameters, I can find find the relation between the non-reciprocity and the topological properties of the system to each boundary condition that I introduced in last slide. So the transfer matrix, if I just redefine the transfer matrix, then I can write the transfer matrix in terms of these two parameters, which Z here is given by the trace of N. And first of all, for kappa less than 1, so then you can have two isolated topological edge states with E1 equal to I gamma, and gamma prime. Sorry, I forgot to introduce them. Gamma and gamma prime are just the complex potential inside the system. For the kappa less than 1, so then you can have two topological edge states, that one of the energies is I gamma, the other is I gamma prime. And if you are looking at kappa D, I mean, if kappa D is is smaller than 1, then the state with energy is E1 is localized at the left. And for the other side, the couple larger than 1, it's localized at the right edge. So this is coming from the topological properties of the system, and I want to show that why these two parameters are important. On the other side, for kappa smaller than B, the state with energy E2 is localized at the left edge, while for kappa larger than D, it's localized at the right edge. And the system is dynamically stable for imaginary E larger than gamma. Why? This is coming from the assumption that I put here. The assumption is that gamma is larger than gamma prime. So the one that corresponding to E1 is the more stable edge state. The other thing that I could find from the spectrum of the system is that there are bulk zero modes with real energy equal to 0. And which means that they are purely imaginary if the system if the parameters of the system satisfy these equations. And remember, the W was the coupling inside the lead, and also it is equal to V prime and U, and kappa here is just the topological characteristic that I introduced to you. So in the following that, when I'm talking about the reflectionless or invisibility, our system is tuned to this parameter that we have two isolated topological edges. Okay, let's look at the reflection transport. Just remind that the reflection transport given by this element of transfer matrix. If you do this, then you can find this equation. So which F is given in terms of the energy, the complex potentials, kappa and W, which minus sign defines the left reflectionless, and the right plus sign defines the right reflectionless inside the system. So I look at this equation in a way that it can give a global mechanism of reflectionless inside the system. The global mechanism coming from the Chebyshev nodes, remember that U was the Chebyshev polynomial. So if you find the Chebyshev nodes, then you can have a reflectionless inside the system. So first of all, it depends on the length of the system, because as you can see, there is L, and L was the size of the system, and it's independent on the probing side. And at E equals to E1 and E equals to E2, Z, which appears inside the Chebyshev polynomial, is invariant under the transformation kappa goes to 1 over kappa. This transformation kind of connects the topological phase for kappa less than 1 and non-topological phase for kappa larger than 1. So in this topological phase, one of them, we have the age state, the other one, we don't have an age state. So what's the meaning of this? It means that since the global mechanism depends on Z, and this Z is invariant under this transformation, which relate two topological phases inside the system. So at the end, you can say that in the global mechanism is independent of existence of age states. So it means that the existence of age states is independent of the reflectionless boundary condition that we can get from the system. But look at the local mechanism coming from F. In the local mechanism, kappa is essential parameter. Why? Suppose that we set E equal to E1. So in the reflectionless, we need to tune the energy of the system and then see if we have a reflectionless effect or not. If we just set E equal to E1, why E1? Because the system is stable and in this energy by the assumption that we put on the system. Then by probing the system from the left, we have the reflectionless if this equation is satisfied. But look at this equation. Inside, on the right side, the omega is the negative. So the right side is negative. And if we want to look at the topological phase, which means the kappa is less than 1, so the right side is negative. So it means that for having this equation, on the left side, we need to have gamma less than gamma prime. But this is contradiction with our assumption, because we assume that gamma prime, the gamma is larger than gamma prime. So what does it mean? It means that if you put the system, if we tune the system, then the system can only be made reflectionless from the left just in the topological phase where kappa is larger than 1. So in that case, the right side of the system is positive and it satisfies our assumption. So in the topological phase, we cannot have a reflectionless from the left. What about the right reflectionless? For the right reflectionless, there is no problem. Because of this minus sign, the right side is positive even in topological phases. So it can satisfy our assumption. So we can say that the system can be made reflectionless in the topological mode. So this is the interesting result, that we kind of relate the topological characteristic of the system to the reflectionless boundary condition. So I need to go faster. If you are looking to the invisibility, which is the combination of the reflectionless and transparent, remember that the reflectionless transport from the right is maintained even when any of the edges set relocalize via the skin effect to the other edge of the systems. So it means that keeping the system in the topological phase and reflectionless from the right, then we can have a kind of edge state. Then we can make the system transparent from the right by satisfying these conditions. D was the determinant, kappa was the parameter defined a topological characteristic. But this equation is important. First of all, if you satisfy this equation, then the system is invisible to the source or to the detector placed to the right of the system, because in the topological mode, we could just have a right reflectionless. But this equation is important because these conditions for invisibility, this condition for invisibility coincide exactly with the skin effect phase transition. It means that for one of them, there is a skin effect on the left side, the other part is a skin effect on the right side. So it means that the transparent channel exactly at these transitions. So this is kind of the relation between the invisibility boundary condition to the skin effect phase inside the system. If you look at the coherent perfect absorber, I will show the picture that make it clear. But before that, just look at the coherent perfect absorber. For the coherent perfect absorber, it satisfies this equation. So it means that the left, if you just solve it for the transfer matrix, then you can get this equation. And this equation on the right side is always positive. So it means that you can have a coherent perfect absorber. So there's no problem of this boundary condition. But the right side is always positive and independent of D, and invariant under kappa goes to 1 over kappa. What does it mean? It means that the CPA can be achieved irrespective of the topological phases. So there is no relation between the system, there's no relation between the boundary condition of CPA and the topological phase. So, but we can make the system and we can tune for example, the parameters of the system to make the system simultaneously transparent from the right or from the left. So it means that we can kind of compose these two effects, coherent perfect absorption and the transparent, and make the kind of transparent CPA inside the system. So this diagram just shows that the summary of the result that we got here. So this phase diagram is given by putting D equal to kappa and D equal to 1 over kappa. So it divided the diagram into 3 regions. That, as you can see, that going from the red to the blue one is just changing the skin effect direction, and this is called as a skin effect phases. And as I showed, this invisibility boundary condition just exactly coincide, with the skin effect phase channel. that separate the two phases that we can have a different localization in different sites. And also this line, the dash one, is defined the region that we can have a transparent CPA. So this is kind of the characterize the invisibility and coherent perfect absorber here. And for the last comment that if you are looking that, okay, so we did everything for the SSH model, can we generalize to the more complicated system? The answer is yes, but this is more technical. And you can use the transfer matrix method that I introduced in last slides and just characterize the system by using the very general form of transfer matrix, which include more links and more internal degree of freedoms. So this is kind of generalization of what we have done for characterizing the boundary condition. So as a summary, so we established a number of distinct transport signatures of non-Hermitian, non-reciprocal, and topological behavior. So the reflection transport in a direction that depends on the topological phases. So it's one of the most important results that we get. And then we show that invisibility coinciding with the skin effect phase transition of the topological age states, as I showed in the diagram. And then we can find the combination of effect that indeed coherent perfect absorption in the system that is transparent when probed from just one side. And thank you for your attention.
Thank you very much, Hamid. Questions, comments? Ali must have a question. No? No, okay. Well, if there are no questions, I think it was a very technical talk. That might be a reason. So let's thank Hamid again. Thank you very much.
Thank you.
Thank you. Very good.
Thank you.